So the last two lectures, we've been talking about policy gradients. The motivation is, can we directly optimize the policy if I parameterize the policy with some parameters? And you can start deriving what the policy gradient look like and apply the modern machine learning workhorse like stochastic gradient-based optimization and throw these tools to optimize the policy. So at the beginning, you sort of take this view that maybe we can set aside and not use these action values or state values for a little bit, just apply gradient descent or gradient ascent at these parameters. Later on, we sort of bring back this perspective of, the variance in the estimation of the policy gradient tend to be quite high. And it's very useful to reduce variance by introducing different sort of baselines. So the baseline is really some sort of function that only depend on the state. So it doesn't depend on the actions. And a very useful choice of baseline to reduce the variance is the state value functions. And that sort of bring back the paradigm of policy iteration where you try to improve the policy, but you first evaluate it, you derive some value functions, and these value functions help you improve the policy. And in policy gradient, you actually enter this picture, the value function enter this picture in a slightly more interesting way, which is more like factor into the variance reduction and lead to different policy update rule that only use the advantage. Okay, so that was in the past. We won't spend too much time talking about that. We'll talk about natural policy gradient. And we'll talk about maybe 3 different ways you will get to these algorithms. And I treat them as pretty interesting interpretation of the same algorithm. The first one is sort of using the stability view So if you remember a few lectures ago, well, in fact, in the beginning few lectures, we talked about no regret learning. One of the key ideas is that you don't want to update your decision rule, your decision making policy too aggressively. Right? So you want to do some slight change, like stable change to your current pi theta, so that whatever you estimated, like the value function, remain valid, or the gradient is still a pretty good direction for improvement. You don't want to go too far. We'll revisit this view of stability or regularization, almost like FTRL, follow the regularized leader. You can almost view gradient descent as instantiation of such a paradigm, and think about whether the inherent regularization is the right choice for policy gradient. Okay. So, and by the way, you also in one of Drew's lectures, you also see this sort of paradigm where the algorithm is called the conservative policy iteration, where the update of the policy tend to be small. Okay, so this is sort of revisiting some of the ideas that's been repeating in this course. Okay, anyway, this is the first view of how you might arrive at this algorithm MPG. There's sort of a regression view. Which I also find to be interesting. This one is much less intuitive. If I just present this as the first thing for you, you find it slightly strange. Like, how is doing a gradient update of some sort doing regression, like least square regression? This is effectively a linear regression. So this is a more nuanced, but maybe more slick view, and this actually opened up some interesting way to design algorithms of other formats. Okay, and finally, if you put the idea of natural policy gradients in the simplest case of the so-called tabular MDP, where when you do a parameterization of the policy, you just use the typical softmax parameterization. You actually derive something that looks like, or the so-called soft policy iteration algorithm. This may or may not make sense, but you think about what policy iteration in the first few lectures of RL is really take the value function or compute advantage function over different actions and greedily take argmax. We know that could be a very bad idea, especially when these advantage functions or value functions are approximated by different function costs. So instead, you don't take the argmax, you don't do the fully greedy update. Here you're basically doing the softmax update. And you have seen this idea before in no regret learning. This is literally doing hedge, like follow the regularized leader, like multiplicative weight algorithms at every single state. So that is a very interesting interpretation of the same algorithm. And related to one of the game theory lecture, this is also reminiscent of this algorithm called counterfactual regret minimization in solving games like poker. Okay. All right, so eventually, all these are just different idealized or theoretical views of the same algorithm. If there's time, we'll like to talk about some practical algorithm. One is called trust region policy optimization. It's sort of related to this view of taking KL regularization, making sure the update is not too big, not too aggressive, maintaining the stability. By now, I don't think anyone really used this. I think it was kind of turning into a different algorithm that you might have heard of called PPO, proximal policy optimization, and there's a lot of attention on this algorithm these days because ChatGPT, like the reinforcement learning with human feedback, this sort of preference fine-tuning in OpenAI use this algorithm. Okay. Although, as I mentioned from last class, there's some recent work showing that you may not need to do such a fancy objective or such a fancy algorithm. The standard reinforcement algorithm might just work. I haven't reproduced those experiments, but take that with a grain of salt to whether you have to use this algorithm. Okay. All right, so let's do a quick recap. It's useful to remember what policy gradient looked like. So we'll mostly think about the advantage version. So there are usually three versions of it. You can write down a policy gradient where, so in each form you will have to play with something like the grad log probability. These objects basically will stay around with us forever. The thing that changes is what get multiplied with the grad log probability. And the thing that the form we'll use for the entire lecture today will be the advantage function. But you can do some recalling from last week. You can also use a total reward or the action value function. So, and the advantage function sort of come out of the action value function because you just subtract off the state value, and it doesn't change the expectation. So you will, by subtracting the baseline as the state value functions, you get this one. Okay. So I will be slightly lazy for notation, so I'm going to define it here. So I often like to pull this summation out. So one way to write this is sort of compress the state distribution across h steps into one distribution, sort of squeeze everything into one single distribution. So here you can almost think about there capital H different distributions. It could be useful to think about the H distribution squeezed into one. So here I'm gonna only have the multiplication between the advantage function and the grad law probability. Okay, so just to be pedantic for at least once, right? So what this means is like I'm sort of sampling a random step. Okay, h minus 1. This means like I just sample random step from 0 through h minus 1, and at every time step there's a state visitation. I'm gonna call this pi theta h. And the action is just taken by applying this policy to SH. Okay? So I'm not going to repeat this full expectation later, but this sometimes is useful. I'm just literally pull out this H front. Okay? Nothing super interesting here. So if you look around online for lecture notes or papers on this sort of stuff, I think majority of the exposition will be in terms of the infinite horizon discounted setting. Almost all the results are the same. Like any result you can derive in the undiscounted setting, you can also have it in the discounted setting. So one rule of thumb, like as you try to read through the literature, you can almost think about in the discounted setting where you have this gamma parameter, that's usually the discounting parameters. You can almost think about all the results, all the bounds you might get, the expression you might have. It's really just replacing 1 over 1 minus gamma by h. So the results almost look the same. So like you expect this to be 1 over 1 minus gamma when people are talking about it, like this infinite horizon discounted set. Okay. All right, so what's going on in policy gradient? Okay. So the policy gradient update looks like this, right? So I want to get to a new parameter that just add some learning rate times the gradient. Okay. The first thing you think of, obviously, you will approximate this gradient with sampling. You might want to do different sort of approximation, whether it's the Monte Carlo one or the temporal difference type of methods. Okay, so we're gonna ignore some of these subtleties here, but really this is the form of the update. What is this one really doing? Okay, so there are different ways to interpret this. You can think about this as doing some sort of regularization update or regularized optimization. Okay. One way to think about this is, well, you know, this could be think of as argmin or argmax, I guess. To optimize the gradient product, so gradient times theta. I want to leave some space. Minus Did you take a picture of me? All right, so why is that? Why are these equivalent?
Take the derivative of the right-hand side, and since the right-hand side is convex, so you just need to make the derivative equals to 0. Then it would be the maximum point.
Got it. Very nice. Let me repeat what you said. This is objective. It's convex, right? So like this is a linear function minus some square. Actually, it's concave because you're maximizing concave function. Negative convex. You know, everything is clean. You just take the first order condition, make the gradient go to 0. If you solve for it, the optimizer actually will be performing this update. Okay. And why do we want to do that, right? So it's sort of repeating the same stability view or slowly updating view, right? At parameter theta t with the policy pi theta t, you have some information, local information to improve the policy. This is given by the gradient. The gradients at some part of a loss landscape point to some direction that can improve the reward. But you know, this is only true locally, so you know, it may not work if you start moving farther and farther away from pi, theta t. So you want it to be constrained quite a bit, right? So you want to not leave the current parameter too much, whilst have an eye of taking the current local information to improve your objective function. Okay, so these are the same. It's really a slightly different view of follow the regularized leader. I think in homework 1A, I guess, the question 1, basically doing the kind of analysis for online gradient descent. And here the regularization is the L2 squared. Okay. And similarly, you can also write down constrained optimization view. So natural policy gradient will follow from this view, but like things like TRPO, like trust region policy optimization will come out of this. But for concreteness, we'll write out both. Keep some space. Okay, so this is penalizing the distance from your current parameter. Another way you can potentially write this is maximizing this inner product with the gradients, subject to a constraint that looks like okay. If you remember maybe the max entropy lecture, there's this object called the Lagrangian. So given any constraint optimization, you can fold the constraint into as part of the objective. You attach something like a Lagrange multiplier. Then you will get the Lagrangian will look like this, except that here you're basically choosing how much you penalize the distance function or the regularization term. The Lagrange multiplier is not something you choose. It's sort of coming out of like, you know, the duality of Max program. Okay. But roughly speaking, if you stare at both of them from a distance, they are kind of the same. Okay. So except that, you know, here you get to choose delta. Instead, you have to choose the learning rate eta here. Okay. But they're kind of the same. All right, so let's take a pause for a second and just look at this. So the high level idea is clear. You want to improve the policy by looking at the gradients, by following along the gradient but you don't want to go too far. And therefore, you will actually introduce this penalty term or this constraint to constrain the distance. Something may feel strange to you, right? So if you start thinking about like what exactly is theta, well, we don't know, haven't talked about it. Theta could be some part of the linear model, could be a transformer, could be a CNN, you don't know it. Moving at some distance in the parameter space, like in the transformer space or the linear model space, it's hard to think about. It's not exactly the kind of distance we really care about, right? So in particular, like it could be the case that even if you have successfully constrained the parameter to not move too much, you might still introduce a ton of changes in the policy space. You might still change like the probability of taking different actions by a lot. Right? So maybe a different, more principal objective you might write down looks like the following. Okay, so more principal objective. Since I'm on the right hand side, I'm going to write down the constrained version of this. Okay. Still, you want to maximize the total reward function or the objective function such that the distribution induced by the resulting policy is not too far from the previous distribution induced by the current policy. Okay, so I'm going to explain what these means in a second, but really what you care about is the distribution over trajectories you might use. You want the trajectory to be not so different, like you don't want the places you travel to be so different. So that you actually maintain this sort of stability, safer update. Right? So how should we think about this? Well, first of all, like you can't quite do this, right? So you can't quite. This is a complicated objective, and you usually don't directly optimize this, right? You, as a single step, you actually use the first order approximation with the gradient. So you can use a different color. This is approximate okay. Just like what we've been doing so far. Let's dive into this objective. It looks a little scary. Okay. Actually, I might introduce 1 over h there. All right, so what's the KL term? Let me define it. I'm going to introduce 1 over h here. So 1 over h KL between the trajectory distribution given by pi theta t and the new policy theta. Okay. So this is a trajectory distribution. Mathematically, I can write it out as a sum. So tau is the notation for summation. So what's the definition of KL? Well, the first argument usually is called the base distribution, where you take average over. And inside, there will be a ratio. Okay, so let me write it out. There'll be a ratio inside along. Okay. So the thing that really depends on the parameters are the action probability under different states. If you write out the probability of the trajectory, it'll be a product of a bunch of things, like at state 0, I take action 0, the transition to take me to the next state. But a transition will cancel out. Okay, so this is sort of in the proof of reinforced, so I'm going to repeat it. But what you get out of this is really another sum. Okay. And the whole thing here, I'm going to use this trick to write this as expectation. Okay. This is really just really the log ratio of the action probabilities between the two policies. Okay. Nothing too interesting going on so far, but the key takeaway from all this derivation is intuitively you only should care about the trajectory distribution. You want the trajectory distribution to be close. One way to capture that, but one way to capture the differences of two distributions from information theory is KL divergence. Right, so this is some of the object we see a lot of times in this class. You have seen it first in Drew's information theory lecture. It turns out that at the end of the day, if you look at these log ratio term inside KL, it really just is a bunch of log ratio term. The ratio is the action probabilities under different states. Okay, let's call this L theta. Right, so basically, if you know a little bit about convex programming, this more principal objective function just saying like you should make this L theta to be not too big. In general, this still looks a little scary. Like you have to compute this ratio and things like that. So, but it is a convex function. If you just look at these probabilities, it's sort of convex in the theta. So you could potentially approximate it, right? So here in the objective function, like before, we'll approximate with the so-called first order approximation. Basically, I just put a linear function here to approximate. You can also approximate this term, this L theta, by something. The question is what to put it there. Okay, so if you look at the first order approximation, okay, of the KL, not the reward objective, that's a key difference. This equals 0 at theta equals t. You have to do the math, like you have to do the algebra. And by the way, also this equals 0, not surprisingly, because everything, the ratio becomes 1 if you plug in the same same parameter. Like if theta equals theta t, like this thing is 0. Okay, so there's actually no information in the function if you plug in the first order gradient. But you actually get some interesting structure by taking the second order information, which is called a Hessian. Actually, I'm going to write it here. Hessian, or basically the second order derivative in a vector space. It looks scary, like, you know, when I take calculus, whenever I see second order, oh God. Like, you first get a vector, now you get a matrix. It blows your mind, like, right? Like, it turns out it's not crazy, and it has a name to it. It's just the gradient. Gradient out of the product and expectation. So this would not be 0, but it would actually be a matrix. It has a lot of interesting structure. We're going to call this f of theta t. This one has a name. This matrix, so it's out of product. So if you put the transpose, this t is not. This t means transpose. Slash intercal in LaTeX. So you put it here in front. You put the transpose thing in front. You get a value, a scalar value. But if you put it as a second, you get a matrix. And this expected matrix has a name. Anyone know what this is?
Fisher.
Yeah. How do you know this?
Just like reading the paper.
You just read papers. Great. Excellent. This thing is called the Fisher. Sometimes called Fisher matrix. Sometimes called Fisher information matrix. Okay. So, okay, let's go back to this picture, right? So, we started this somewhat more idealized objective where you control the relevant distributions, right? You want to control the relevant distribution so that it doesn't change too much. Instead of thinking about some raw parameter space, that the relationship between theta and the induced distribution may be unclear. Okay. So you can approximate everything here, so you can actually get something like max of same gradient of the objective function. Okay, such that, so this one you can think about as some quadratic function as well, like this is directly Euclidean distance, which is also some sort of quadratic function. Here you can think about this as C. I should put the image. Okay. So with the quadratic approximation, with given by the Hessian of the KL. So let's try to really approximate this term. I guess something like this. So this is the second order approximation. And we won't quite work with this view too much. The point is, you can also back out further into what you know as this regularization view, and eventually the update rule, the raw update rule, it looks like. The takeaway is, I'm going to skip the regularization view, is basically putting this quadratic function in the objective with some multiplier. The natural policy gradient update is really taking into account the shape of this matrix. By the way, like if this F happened to be the identity, these two things are the same. If this is like the identity matrix, these two constraints are exactly the same. The F, the Fisher matrix, is really just reshaping the geometry in a certain way that is relevant to how you might change the distributions. And if you bring the information, the Fisher information matrix, all the way into the policy gradient update, or the natural policy gradient update, you get the following rule. Okay. Do you know what this is? This is not T, it's T but with the bar shooting up above the bar. It's a dagger? Yeah, excellent. What's the dagger for? I mean, there's an algorithm called dagger. Very good. You learned something from, where do you see this?
Inverse kinematics and stuff.
What?
Robotics.
Robotics. Excellent. I never remember what it is. Like I know, like, oh yeah, pseudo inverse, like this dagger thing. Like, okay, so this is sometimes called, what's it called? I wrote this down. Oh yeah, Moore Penrose inverse. Yeah, so I almost always forget how it's defined. So my lazy self just think this is the inverse, the matrix inverse. The only caveat is that the F itself may not be full rank, so inverse is not well defined. For the sake of this class, just think about this as inverse, but like if you really want a formal definition, like usually you do this eigenvalue decomposition, which looks like some matrix like this, right? So like F is some, if you know linear algebra, it's called like, positive semi-definite and like symmetric. It can be factorized in this form. This pseudo inverse is just saying like you do inverse where you can, like you just. So the only thing happening here is like you keep the U matrix, which is really some form of rotations. This is just like a diagonal matrix with some values on the diagonal. But when F is not full rank, some of the entries are 0. You just apply the inverse to where you could apply, meaning like you keep the zeros around and you take the inverse of the diagonal values. That's non-zero. Okay. This is only for people who like to think rigorously about math. Some of my students don't. But just think about inverse if you're afraid of linear algebra. Okay, but the punchline really is this is the algorithm we're interested in. I spent a lot of time. Oh God, I'm behind. This is the natural policy gradient methods. Okay. So why is this interesting? I'm going to quickly show you an alternative view of how you arrive at this. This is a strange view that it may not be intuitive at first, but it will be useful for deriving some different output. So what you saw before is essentially the regularization view. So I'm going to present a regression view. Okay, so the first few times I heard about this pseudo-inverse concept was linear regression. It's basically like, this is like a tricky case where maybe the matrix of the feature vectors don't exactly span the full space. You have to be careful in taking inverse. So this pseudo-inverse also showed up in the regression view, obviously. Like, by taking this pseudo-inverse, it's implicitly hinting at some linear regression procedure. Okay, I'm going to write it down. So suppose I solve the following regression problem. So think about W as the same space, living in the same space of the gradient, or the parameter space. Okay, so I have the advantage function kind of as the target. Minus the grand log probability. Square. Okay, so I'm writing down the square law subjective. And pretend this is sort of like the feature in a regression problem. The target is sort of like the label. You don't have to think about it this way, but like, that's how you map it to a regression problem. Okay, so the update, which involved like the Fisher information matrix times the gradient of the objective, it turns out this is the same as the regression parameter come out of this. Okay. This holds for any theta. This is drawn from d pi theta. Okay. So this h is just a scalar. Okay, Let's prove this because it's two line. Okay, so this is just a squared objective, right? The parameter is like W. So this is like, it looks scary because like this pi theta could be like a transformer, it could be arbitrarily complicated. But all you're optimizing is the W. Right. So this is like a regression way to compute the gradients. And in a lot of in practical scenario, we actually would prefer to perform this. So the first order condition give you something like the expectation. So you take the derivative, so to speak, the gradient, which is A of okay, so by chain rule, I first take the 2 out. Like something square would be like 2 times something the gradient. And the end, I also need to take the gradient with respect to W inside this expression, which I just get the gradient of grad log. Okay. I want to set this to 0 because I know W star minimize it. Okay, so there's something I can do here. Like there's an expectation outside. The expectation is over state action pairs. These are random. These are random state action pairs encountered by rolling out policy pi theta. W star is a fixed quantity, right? So it's the optimal solution that's fixed. Okay, so there's something you can do. First of all, like I can probably move W star outside of expectation, being a fixed quantity. And second of all, like I can just move some of the terms on the other side of the equality. Let's do that. So on the left-hand side, I get something like advantage equals one out of space. Look at this. Okay, just enough space. Missing some H here, but you can figure it out. Like this. Okay. So nothing fancy here. I'm just like pushing this on the other side, but pulling W star out. You have to make the matrix vector multiplication work out. Not too interesting there. Stare at the two expressions, and you realize these are things that we have encountered before. Okay, so what is this thing, right? Like this is the advantage times the grad law probability. Where have you seen this before? Advantage times grad law probability.
Baseline.
What's that?
Policy gradient with baseline.
Policy gradients. Okay, so this thing is really the policy gradient. There's some rescaling, I think, by 1 over h, because there's usually a sum over h outside. What's this thing? It's expected of some outer product. Oops, too much. Okay. It looks familiar. What does this say?
Fisher.
You're on fire today, man. Excellent. This is the. Okay. So this is really just the F matrix. Okay. And you can sort of back out W star by this expression. So W star is just like you multiply a pseudo inverse on both sides, on the left on the left. Okay, sorry. So you can multiply F beta here. Okay. And the only thing that matters is you have pseudo inverse multiplied by its own matrix, you get identity. Okay, so it's kind of like acting like inverse even when there's no full rank. What you get is sort of the expression in the lemma. Okay. So, why is this an interesting view of what natural policy gradient is doing? So, if you take the regularization view, the regularization view is saying like you should take small steps, but you should take small steps in a meaningful way. Like, in particular, you should take small steps ideally by controlling how much you shift the trajectory distribution or the probabilities of taking different actions. Okay. So the regularization view is sort of like a stability perspective. You want to be stable and somewhat slow, be a little bit conservative. The regression view highlight a few other things. One thing that is interesting is sort of an invariance perspective. That's why some of this algorithm is sometimes called covariant policy search. So okay, so what does that mean? So invariance property, well, so we happen to choose some theta space. We happen to work with some way to parameterize the policy. You may not, if you wake up the next day, you may not think of the same raw feature engineering. You may not come up with the same model of the architecture. You might, work with a different space. So like, you have the original space. Maybe on a different day, depending on the mood, you might work with a different set of feature that is, some sort of affine transformation or linear transformation. Okay, so there, go. Linear transformation. Right? So it could really happen, right? Like, suppose you are using a linear model to decide how to parameterize these policy. Maybe a different person could have used, a different units when they're measuring the state action feature. Right? So in general, you can think about this capture different kind of rotation, rescaling, scaling. Okay. In principle, you should not think of anything being changed, right? Like, if I take something like a picture, I rotate it, maybe I make the color more stark by multiplying the pixel values by some scalar value. I'm not changing the information in this picture, right? So this is the same idea here if I have a parameter, but somehow I decide to work with a transformation of this parameter space. Like I might just decide to add a constant, rescale by some value, do some rotation, etc. Like the way I update the policy should not be changed. It turns out if you perform such a transformation on the parameterization, As a toy example, think about multiply all the parameters by a factor of 5. Okay? Policy gradient will lead you to a very different policy. Like the policy gradient method will take the transformation you give it, and even though the starting point of the two parameterization is the same policy, policy gradient will push it to a very different policy, like in the sense that the resulting action probabilities will be very different, and therefore the trajectory you observe will be quite different. Natural policy gradient would not. Like natural policy gradient had this property called invariance. Basically means like no matter what A you provided, like maybe A is identity, maybe A is some rotation, something complicated. The resulting update, the resulting policy from natural policy gradient update will give you the exact same policy. Okay? And how would you see that from this lemma? Well, here's one way to see it, right? Like, if I decide to perform some rescaling on theta, I just, I wake up one day, I have a beautiful idea, like, I just decide to use a different parameterization of policy. So we involve multiplying by some matrix. Okay, so if you look at this regression problem, previously you were taking gradient with respect to theta. Now you switch parameterization, so you would take the gradient with respect to phi or 5, depends on how you pronounce it. But the regression problem is sort of taking care of this rescale, because by chain rule, the switch of parameterization will just like there's like sort of like a multiplication of A in here, because of reparameterization. You would just lead to a different regression solution that would take it to the same minimum objective. As a result, the policy will actually be the same. Okay, the resulting policy will be the same. Okay, and that's sort of another nice property of natural policy gradient, in the sense that when you take the Fisher information as the approximation for KL divergence, you also introduce a way to shape the space by rescaling different dimensions in certain ways, so that this sort of reparameterization doesn't matter. Like, you might hit your head the other day and you come up with something different. Don't actually hit your head. You have a different idea the other day, you might have a different way to parameterize the model, the policy. It doesn't matter, because like the Fisher information is sort of taking care of the relationship between the parameter space and the log probability space. And the regression lemma is sort of one way to see this. Okay, so let me present one final view, and yeah. Probably will run out of time. So the natural policy gradient is also a way to interpret a more stable, more robust form of policy iteration called soft policy iteration, that instead of taking argmax the greedy update, you just do some sort of softmax update that look like the hedge algorithm. Okay. So I'm going to think about the softmax. So I'm going to think about some parameterization in the tabular case. When I say tabular case, it really means like the state space is somewhat small. You can afford to write down a different number for every state. Okay? So here you just have pi theta. Probability just proportional to the exponential of theta s. Okay, so the parameter here. Okay. So for every state action pair at every step, there's some parameter that looks like this. You're just taking the softmax. Okay. So this is just another simple example of how you parameterize the policy using parameter theta. You can also apply the natural policy gradient to this setting. Right. Turns out that you can actually show this is just soft policy iteration. Because you can show that the theta t plus 1, when you do the update, it will look like this. So this is the advantage of the current policy. Okay, so what does that mean? Well, you have to, so this is happening in the raw parameter space. You have to plug it back into the softmax. This implies the new policy after the update will just be a slight multiplicative change of the last probability. Okay. So this is the update in the raw theta space, like you just have to work out the math. What's more interesting is here. Okay, so at every state, SH, I guess like technically you will parameterize the state at different time step differently. The point is you originally have some probability distribution on how to choose actions. And the advantage you learn for current policy provides some way to improve, right? So there's some way to improve, by evaluating these advantage functions. In practice, you'll probably need to learn these quantities, but idealized setting, someone evaluate the policy for you. In the tabular case, it give you this A. Okay, and this is just like a hedge update, where you slightly change the probability of taking each action A by multiplying with the exponential. And what's inside the exponential is some rescaling of the advantage function. Okay? So this is sort of the same as the hedge algorithm, except that you're actually running many copies of it. Like you're actually running a hedge algorithm at every SH. Any question about this? So one cool thing is that, this is sort of reminiscent of some of the algorithm in the game theory class, where in the, sequential game setting where, you're playing something like poker, you will walk down some game tree, you will arrive at different SH, like literally these SH in a poker game will be different states at different time step. The kind of algorithm people use to solve poker, or kind of factual regret minimization, is running a no regret algorithm at every tree node. Like every tree node, the player get to make a decision. You instantiate some algorithm like hedge, like multiple weights or FTRL at this game node. And you can actually solve the game, and you use no regret algorithm to approximate the equilibrium. And here is the same idea. You just think of in the tabular case where you can afford to write down these different parameters for different state actions. this is the same idea of like running hatch at every state you might encounter. Okay. Obviously, the practical algorithm would not actually do this. You will introduce different functional approximation. But this is like one way to actually do policy iteration. So instead of doing argmax and put all the probability into the action with the largest advantage, you're doing this softmax update that gradually shift the distribution. And this is something you can actually get provable guarantee. Okay. And also this is usually how you derive the theoretical algorithm and apply different sort of practical approximation. Okay. So I won't prove this. What's nice about this soft policy iteration view is that if you stare at the regression problem above, you realize this just come out of the regression view. So the proof idea if you take the regression, stare at the regression, above. Okay, just like let's actually look at it for a second. And then you realize, I guess I realized before, W star is sort of the advantage. So therefore, the resulting update looks like this. And that become part of the exponential in the softmax update. Okay, I have like 5 minutes. We'll talk a little bit about PPO or TIPO. So these are algorithms they're sort of motivated from the interpretations of natural policy gradient, where you want to make meaningful changes to the parameter space so that you actually get some sort of stability in the resulting action probabilities. Okay. So one type of objective, which is not exactly the same as what you operate from above, looks like this. Right? So I'm hiding some H everywhere to save time. Okay, so where does these SA pair come from? You can think about it come from like some data set that provides some sort of SA and also some estimated advantage function, advantage values from the rollout of the current policy theta t. Okay, so you roll out a policy, you gather some state actions, you visit it, and you can use some sort of critic method to estimate these advantage functions. Okay. So if you put some sort of constraint like the KL constraint, this sort of becomes the so-called trust region policy optimization. Okay, so a 1 minute explanation of why this is a good idea is, well, the advantage function sort of measure where you can gain improvement by putting more probabilities on certain actions. Okay. One tricky part is that when you switch from pi theta t to pi theta t plus 1, you will actually face a different distribution that will look different. Okay. You want to make sure that when you switch to a new distribution, the improvement still remains. So there's a distribution shift as you update your policy from theta t to theta t plus 1. And this is what the ratio term is doing. So you basically reweighting the data you see by whatever new policy you might come up with over the policy you currently have. So this probability ratio capture how much weighted advantage you will get for the new distribution. And you also want to make sure that the same sort of stability perspective, you don't want to update the policy for too much, because then these value function or the advantage functions remain valid. Okay. It turns out this is not what people do. There are a few reasons, like this tend to be hard to compute. You can approximate it with the Fisher information matrix, but even then you have to do a lot of matrix vector multiplication. What people tend to do, that's called PPO, that tend to be a bit hacky. Okay, so I'm going to make some space here. In my opinion, it's kind of cool someone come up with this algorithm. It's not the most elegant algorithm. Okay, so let's start with this objective. It captured the idea of, when I do the reweighted, I actually capture the right distribution. But when you see something like this in the objective function, you should be a little anxious. Density ratio can be crazy large, especially when this theta t is pi theta t could be very small. Okay, so there's a clip objective. So we often heard the word clipping. Usually it means the following. Means like I make sure this probability ratio is not too insane, and you stay around 1. And then it's basically the same objective, but I control the behavior that might come out of this probability ratio. Okay? And this could be wildly large values that you may not want to see, like it will make the optimization highly unstable. Okay? There's one more step, like the actual PBO objective is sort of a interpolation between the clip objective and the TRPO objective. It really just is the minimum. A lot of repetition of the same symbols, but nothing too interesting. You're really given what a clip objective is, just sum over the data points. I just, instead of sum over this, I'm gonna take a minimum between the TRPO objective and the clip objective. Okay. So there's some success of using this for robotics, and obviously, according to OpenAI's white paper, this is used in training ChatGPT. It feels a little hacky, but introduce several ways to ensure that you're only updating within the trust region, really. Like, this clip objective sort of penalize large density ratio, right? Like, a large probability ratio, right? Like, the way you read this is if this is too big or too small, the clip function will just collapse to either 1 minus epsilon or 1 plus epsilon. So if these quantities are behaving wildly, the clip objective is just saying like, forget about it. It will only look at 1 minus epsilon, 1 plus epsilon as a constant. And once you do that, like, there's actually no more thing you updating. You just flatten out the parameter you control and stop pushing away or in certain direction on the parameters in a way that might influence the pi a's condition mass. Okay. And the minimization is just like coupling the minimization, like, in case this get flattened out, you might still want to have some improvement sometime. For example, when the advantage is positive, and the ratio make this to be a smaller quantity than a clip objective, which can happen, right? Like, maybe accidentally you make this density ratio like 1/2. It's not a wild value. There's still like direction you can improve. So when this is 1/2, this will pick up to be the minimum term. There's still reason and good direction to improve it without hitting these wild values of the probability ratio. Okay, so feels a little hacky, but has a lot of empirical success. And I think Gokul wanted me to mention that a lot of the hyperparameter tuning of how you choose the clip parameter, happen to stay the same for robotics and also something like language models, which sounds pretty remarkable. A bit over time. I will see you on Thursday. And please start on homework 1B.